The Sun Corridor is the fastest growing megapolitan area in the United States, with rapid population increase and urban expansion, and it impacts, obviously, the quality of life of many millions of people. And so the Sun Corridor is in a unique position because it can guide growth in a sustainable fashion, and it can become sort of an epitome of how smart growth is supposed to occur. We utilized projections of Sun Corridor expansion out to 2050, middle of the century, and implemented these different scenarios of urban expansion located in Arizona into our numerical model. And then we repeated those simulations with a maximum Sun Corridor expansion scenario and a more constrained minimum expansion scenario. In totality, we conducted about a half-century of numerical experiments, continental scale numerical experiments, including all the different adaptation scenarios and Sun Corridor growth projections. That's at 20-kilometer resolution. That's quite a bit of computing power that was necessary to accomplish this task.
Here at ASU we are very fortunate. We have high-performance computing center with over 5,000 processors. It's like sort of imagine 5,000 computers, 5,000 PCs connected, and in parallel doing climate simulations. We are able to run several initial conditions and obtain to resolve uncertainty in our forecasts. So we have urban heat island effects, but also climate hydrology impacts.
The adaptation scenario that we implemented was basically utilizing what are referred to as cool roofs, where you raise the albedo or the reflectivity of the urban landforms such that much less of the incoming solar radiation is absorbed. And of course, previous research has found that that leads to a considerable cooling effect. But in addition to mean surface temperature, or average surface temperature impacts, we also need to extend our analysis to the hydrologic cycle. And what that means is that basically you have rainfall that in a normal manner, once it falls into the natural land surface, it is held in a similar way that a sponge holds moisture, it is held by the soil-water column. Now, if you pave over this entire geographical expanse, you are now forbidding the land surface to act as a sponge the way it normally does. And so by modifying the regional hydroclimate in this manner, what you're doing is you're basically decreasing precipitation, averaged over the entire year, considerably. What we're emphasizing here is that indeed, if you implement on a large scale these cool roofs, that you need to assess trade-offs that extend beyond just averaged temperature. And in this particular case, what we found is that precipitation, by implementing this adaptation approach, cool roofs, does in fact modify the hydrologic balance in such a way as to decrease regional precipitation considerably. I think we need to extend our research, perform more research, and to try to highlight what these additional possible adaptation and scenarios, mitigation scenarios are, and then with additional research to better understand what the trade-offs are.